Hi, I think we can start. So everyone, welcome. Good morning. And this time we're still talking about relativity. And last time is basically what we went through last time, but we noticed that it was probably very mathematical. This time we'll take a conceptual approach, and then if you're interested in more math, we will have more resources for you. But mainly we'll talk about concepts. So let's start with our photo and our news.
So today our news is regarding gravitational redshift, and it's about general relativity. So gravitational fields can distort spacetime in general relativity, right? So we had researchers from the Institute of Astrophysics in the Canary Islands, and they were exploring this actually. They were seeing a shift to longer wavelengths in the spectrum of the sun, right? And so this is predicted at about 2 millionths of a wavelength by Einstein's calculations. And this is difficult to measure. And so the scientists used the solar spectrum reflected from the moon, and they used something called HARPS, high accuracy radial velocity planet searcher. And they were able to measure the position of iron lines in the solar spectrum according to gravitational redshift. And you can learn more about this at the source over here, which you can see when we release the presentation. And here is another cool photo regarding gravitational redshift. And it's from a different system. It's from the star system 4U1916053. And it's with two stars in close orbit, right? So one of them is the neutron star, which is formed when the large star will collapse into a supernova. And the other is the core of a star with some outer layers stripped away. And so this is from the Chandra Observatory. And this is an analysis of the X-ray spectrum. And you can see I have the byline for the image right here, gravitational redshift of X-ray spectrum for iron right here, which is what the graph above is showing. And again, we're going to longer and redder wavelengths. And this is due to a loss in energy and lower frequency.
Now we're going into our series of special relativity. It's a session 2. As Alan has said, it's a more conceptual approach. So first we need to talk a little bit about the frame of reference. So the frame of reference, inertial frame of reference are a frame of reference that's at rest or is moving at constant velocity. And the non-inertial reference frame are accelerating. And the special relativity only applies to the inertial frame of reference, which means that the things cannot be accelerating. They must move in constant velocity or they're not moving at all. So this is a review session. Okay, so let's first go back to the beginning. So as I have said in like our second physics presentation, we mentioned the two dark cloud on physics. So one of them is the black box radiation, then which later becomes the base of quantum mechanics. And the other one is this, the Michelson-Morley experiment, which will be the base of relativity. So the Michael-Morley experiment was an attempt to detect the existence of the luminiferous ether, a supposed medium permitting space that was thought to be the carrier of light wave. So because we usually saw that wave needs to go through some kind of medium, and the scientists naturally consider there is some matter that is called ether that is consists of all the universe. So that's how light can travel through it. So they made an experiment trying to, so since Earth is revolving around the sun in a constant speed, so Earth must be moving in a constant speed through this ether cloud. So Michelson and Morley, they conduct many experiments to try to detect the Earth's speed in ether, but but what they get is that the Earth is moving in a much slower speed than they have expected, and more experiments gradually shrinking down that speed closer to zero. So it proves that the Earth is not moving Earth is not moving in the Aether cloud, and that's furtherly proven that the Aether theory was wrong. So nowadays scientists consider that Aether does not exist at all, and that the light speed is throughoutly constant throughout in the vacuum. The principle of relativity. So all the ideas from special relativity were based on one principle, the principle of relativity. The principle of relativity first basically it says that physics laws are same, and no matter which reference frame you are in, which inertial reference frame you are in. For example, if I am in a train and someone else is on the ground, neither of us have any method can have any method like doing experiment to see whether we are moving or not, or we are still, because they have no difference. So another basic theory you might heard about is the light speed is a constant, but it can also be explained through the principle of relativity, because the light speed is a constant no matter which reference frame you are in. So Lorentz factor. People usually make assumptions that time is absolute throughout the space, because that's naturally what we expect of time. It's independent from any influence. But the idea that no matter which reference frame you are in, the light speed is constant, it actually changes the idea. So look at the figure above. A pulse of light travels through a distance of 2d in a period of time t. So now in the figure on the right, imagine this system is moving towards the right. So the light needs to travel a longer distance, not just d, it becomes L. So in that case, the lights, if we are still using the concept that the time frame for both figure are the same, then the light speed must be faster than the light speed must be faster than the light speed must surpass c. So but as we have known, light speed is always a constant. So instead we need to make a small change to the time. So the process of calculating this new time is quite simple. So notice that there's a right triangle with side L, D, and 1/2 VT. So we can use we can use Pythagorean's theorem, and we can find out the time. So first we find first the original time is 2d divided by c, and the changed time is 2l divided by c. Then we use the Pythagorean theorem, and we can get the result. And that is the Lorentz factor. And Lorentz factor Lorentz transformation not only applies to time, but also to an object's length and even mass. So on the right is a graph of how Lorentz factor changes as the speed of light, as the speed changes. So as you can see, when the speed is relatively short, relatively slow, when it's less than less than the speed of light, is really low. So it's hard for us to distinguish this difference in common day life. But as the velocity approaches towards the speed of light, the Lorentz factor get increased to the infinity.
This is some basic intuition regarding the Lorentz transformation. This is kind of the geometry behind the transformation. And the key point here is that the speed of light is always preserved. These kinds of Lorentz transformations will always preserve the lines, which are the speed of light. And on that vertical axis that's moving is time, and the horizontal one refers to space.
Okay, so let's talk about space-time. So last session, we talked about space-time, which is a combination of space and time. And we know in our world, we have like three dimensions, three spatial dimensions. And we can use like X, Y, Z to represent where a point is located. So we know we all experience time, right? So we can add this axis to our three-dimensional spatial dimensions. So this is called space-time. So here, these two pictures are can represent space-time. Like for example, if you have a rocket that travels at 25% the speed of light, you will have the blue line in here. And if you have it travels at 50% of speed of light, you will see the green line on in here. Actually, the upper one. So if you emit a beam of light, you can see it as the yellow line in here, right? So this is about space-time. And can you go to the next slide? Okay, so let's talk about the light cone. So similarly, light cone is a three-dimensional representation of space-time because there's no way for us to visualize a four-dimensional space-time diagram. So we use such diagram to represent space-time. And as you can see on the right, the vertical axis is time, and this is what you will see in the future, and you see there are two cones. The upper one is called the future light cone. This is what you will experience in the future, and on the one on the bottom is the past light cone, and everything that is located in this cone can be the cause of your present states, right? So can you go to the next slide? Okay, so Minkowski in 1908, he reformulated Albert Einstein's special theory of relativity. So the diagram, the light of light cone is usually considered the Minkowski like geometry, and okay, I'll go to the next slide. So because you know we know the time is dilated if an object is travels, and we have to use we know like in three-dimensional space, the distance between 2 points can be calculated through Pythagorean theorem, but because in space-time, we have to use another concept. It's called proper time interval to describe the arc length or the distance in space-time, and it is calculated through this formula, and let's go to the next slide. Delta S. And so if delta S is less than 0, that means the spatial separation is less than the distance that travels. So it'll be located into the light cone. So this is possible, right? Our scientific law allow you to do this. But if delta S is 0, that means you travel as fast as light does. So this is called a time lag. And if delta S is greater than 0, that means the spatial separation is greater than the distance that light travels. So the interval is called space lag. So it's actually our universal laws do not allow you to do so. This is
So-
called space, yeah,
So
space
what's
lag.
outside of the light cone is undetectable and unknowable for us because information nothing can travel faster than light. So if the light emitted by something haven't reached me, there's no idea for me to get any information from it. So for example, let's say a supernova explosion happens 100 light years away from us, but the light has to go past 100 years to reach Earth. And before that, we have no idea of knowing whether this supernova explosion happens or not. So it is quite interesting to think about it because we can neither control nor detect things outside of our light cones, but we can only choose how we cope with information inside the cone. But it is up to destiny what things they are going to put inside that cone.
Okay, thanks, Alex. Okay. Okay, let's talk about twin paradox. This is actually not a paradox. That's why I put a quotation mark on. So, for example, if you have a twin, so suppose the first the one is called the observer is called A, and he stays on Earth, and his space-time coordinate is just 0, 0, 0, 0. So the first number represent the space, the time, and the rest of the three are the spatial coordinates. And so if if A stays on Earth for 10 years, the proper time interval for him is just 10 years, right? Because there's no spatial coordinate change. And if B, let's see, there's another observer who travels in the x direction from Earth to to 5 years, 4.33 vectors, 0, 0. So that what does this mean? This means that like he goes there. It takes him 5 years to goes to another place, and and he comes back after another 5 years. So because of the relativistic effect, the time he actually experienced is dilated, right? So we can calculate how much time he experienced through the formula here. Like square root of 5 years minus 4.33 years square. And finally, we will see it's only 2.5 years. That means if A stays on Earth for 10 years, but if someone like travels on a rocket and comes back, he's only getting 2.5 years older, right? It's really interesting.
So the reason this is called the paradox is because the idea that there's no absolute frame of reference. So if I am moving in like very close to light speed and Bohong is staying on the ground, if he relative to me is going at a light speed because we have no actual frame of reference. So if this isn't the case, then both of us will expect to see other as a younger person than us because we assume that we are the ground reference and he is moving in close to light speed. But what solves this paradox is the idea that the observer observer A is not accelerating, but B, it actually accelerates. And this accelerates, as we have said, is the non-inertial reference frame. So that non-inertial reference breaks the idea of the special relativity. So it's actually, B is actually B experience lesser time. So B becomes younger than A.
So you have to pay attention to who's actually accelerating in this situation. Yeah. So let's go to the next slide. And now I'll conceptually introduce some math behind special relativity. As we know, we just talked about the proper time interval. So we can write it in the differential form. It's ds squared c squared equals c squared dt squared minus dx squared dy squared dz squared, and we can use the matrix tensor nu nu v no mu nu dx mu dx nu to represent like how the space time is curved, and the 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 image the formulas on the right is if you guys have taken calculus, you can use the integral to see like how much actually how like it's like how much you time or how much distance like you have like experience if the speed of an object changes over time. And yeah, this is actually the integral form of space-time interval, as you guys can see. And I think yeah, that's it. And thanks so much for listening. And I think next session we'll be going over some general relativity, and it'll be much more interesting and much more exciting.
Okay, that's great. And I hope you enjoyed it. And here's the link for the physics news. And we have some time for questions. So please unmute or type in chat if you have any questions. And we will post the slides. So there will be like equation for like the mu matrix. That was in the slide, and so you can all reference that. We have 5 minutes left, so if there is any question, I mean, we can play a video, and yeah, so.
Yeah, let me know if you have any questions about the math behind the relativity. Yeah. And yeah, I'm so happy to talk about it. Yeah.
So email, Discord, or yeah, of course, in the meeting will be a great place to ask those. We're checking them every day. And Mr. Nauman, could you give me the screen share permission, please?
Rohan's host.
All right. I'll send the video link in the chat, I think. So it's a video about inertial reference frame, a little bit about, yeah. And then it has a pretty cool visualization of light clock. And it's the basically light being constant and the basic idea of special relativity.
Sorry, Alan, my Zoom locked up. I couldn't unmute myself.
I think I can stop the meeting recording now.